The image next to me is of the Greenland ice sheet, one of only 2 ice sheets in the world. You can stand in front of the edge of it, in front of glaciers that stand 100 meters high. My name is Meghana Ranganathan. I'm a PhD student in climate science at MIT, and 3 years ago, I stood in front of one of these glaciers. The scientists I was with told me that when you stand in front of this glacier, if you're really quiet, you can actually hear the ice creaking as it flows. Except I couldn't. When I stood in front of this glacier, all I could hear was meltwater. The rushing of water coming from the ice sheet through the town of Kangerlussuaq and into the ocean. Over the last 10 years, flooding has become an increasing problem for this town of Kangerlussuaq, which has the only international airport in Greenland. It's become such a problem, in fact, that back in 2012, flooding threatened to shut down the entire country. When we walked away from this ice sheet, from the glacier, my tour guide, who is a native of Kangerlussuaq, stopped our tour, turned around, and held out his hand. He was holding a mosquito. Now, I didn't think too much of this at the time. I'm from Texas, those things are everywhere. But in Greenland, mosquitoes aren't supposed to come out until June, and this was mid-April. Later, when we finally got a chance to walk up to the ice sheet, as you see in the picture, we walked past these hills of sediments that run in a ring around the ice sheet. That sediment marks where the ice sheet used to be in 1999, and you can see how far it's receded since. That's the power of being in a place like Greenland, where everything, the landscape, the biology, the society, is altered by climate in a profound way that we just don't see here on a day-to-day basis, at least not yet. And that's why the MIT approach to earth science is so important, because at MIT, the earth science department is one department under which geologists, meteorologists, glaciologists, and geobiologists can all interact and collaborate on a problem that is really at the foundation and at the intersection of every aspect of earth and life sciences. And then there's people like me. I study applied mathematics and machine learning. And increasingly, this is a problem that people like me need to help solve. Because it's not just Kangerlussuaq that's seeing the outcome of these changes. Every area in the world is seeing the fallout of climate change. But every area in the world is seeing it in such drastically different ways. And right now, we just don't have the ability to represent how local climates are going to change. And here's why. The way our climate models work right now is on a grid format. We overlay the entire Earth with a grid. And between each grid boxes, we can represent the wind that flows from one to the other, the radiation that enters a box, and the radiation that leaves. But what we can't do is we can't represent anything that happens within a grid box. That's a huge problem, because so much important phenomena happens at scales smaller than our grid boxes. Right now, the quality of our climate models is incredibly dependent on the size, and because of our present computing power, those boxes are about 100 kilometers squared. So one important phenomenon that these grid boxes and these models can't represent are clouds. Clouds form and change at scales smaller than these grid boxes. And that's significant because clouds set so much of our global climate. Clouds set the radiation that reaches the Earth and the radiation that bounces back out. Clouds set humidity, temperature, and precipitation, and all of that is important for understanding how local climates will change and for our global climate. And right now, we just don't have the ability to represent that. This is where MIT and machine learning come in. We're attempting to embed each grid box with neural networks that will enable us to represent the small-scale phenomena in a computationally efficient way. And if we can accurately do that, that could change everything. If we can represent that small-scale phenomena, we are a huge step closer to understanding exactly how the climate of Los Angeles will change in 100 years, or the climate of Kangerlussuaq, Greenland. And that will help shape our responses. Climate change is a tough problem because it's not a question of the world ending. The world will always survive. But our societies have been impacted by climate in huge ways in the past, and our present-day society is set up for a climate that we no longer have. The work being done at MIT is intended to advance our predictive power so that we can find local solutions to the changes in local climates, and so we can inform our global solutions. Because at the end of the day, we're not looking to save the world. We aren't even looking to save the glaciers and the ice sheets in Greenland. We're working to save ourselves, to make a better world. Thank you.